from satellite level. The Doppler count will be the same if I say, and here instead, the time that the satellite has, it takes time until it comes to the receiver, and this time this is a function of the distance between the satellite, the first satellite, and the receiver. Let me call the receiver K. Receiver I, sorry, receiver I and 1 over C, and Tj, for example, will be difference between I and J receiver. What does that mean? It means that if I have an orbit and I have a receiver here, when the satellite at its time, let me say Tj, sends the signal to receiver, it will come here at this time. Actually, it will be Tj plus Rij, or if it is I, over the C. So why? Because the speed of the signal is the speed of the light, and then if I divide the speed of this distance from satellite to receiver by C, which is I come to the time difference, it means that actually this is the travel time from the satellite at the position J to C. If I have satellite position K, then I can write that the time that the satellite has been on the way to will be R I and K over C. So that's the point. How can we get position out of it? Let me draw a figure for you. I have a coordinate system, X, Y, and Z, and I have a point P at the surface of the Earth, and this point has position Ri, for example, in the Earth's coordinate system. And I have a satellite pass over the area, over this position. Let me call this position J and this position K. And the distance between this J and P are called I and J. Let me call this I point, which is P actually. I, J. And also I have this distance, I and K. So the problem is to find the relation between the Doppler count and Doppler shift and actually these two ranges. How do we do that? There is a condition that should be fulfilled. The time that the transmitter sent with the frequency S dt should be equal to the time that comes to the receiver, the Doppler count. So it will be C and it will be Tk plus the time that this has been arrived and frequency has received at the receiver. So that's the point. This condition should be fulfilled. This condition fulfilled. If I put it back inside the Doppler count equation, the Doppler count J will be, so as we see, Tk minus Tj is the same here, and I can write. We're almost there. We have a mathematical relation between the Doppler count and the range. And range can be written in terms of the coordinate. So the Doppler count between the satellite positions I and J, Doppler count and R, J and K, sorry, J and K is the satellite position, these two positions of the satellite. Then it will be unknown parameters are coordinates of the receiver plus this term. which is the shift from the generated signal at receiver and the source signal, source frequency. So that's the principle for Doppler positioning. The coordinates of the satellites are now at 2 positions, and this term will be constant because we have only one source and one receiver, so it can be estimated. And Doppler count actually is the observed measurement. So this means that if I have a receiver like this, antenna here, I have satellite pass. After a while, we will have redundancy. So Doppler count, let me call 1, 2, 3, 4, 5, 6, 7. Then you can determine the coordinate of the receiver in a list question. So we have Doppler count if I, J, and K is like that. One unknown was this one, and we have delta T, the time between. If you remember, and we have FG, this is the generator, and we have 2 ranges on them. Satellite coordinates are inside, and they have also receiver coordinates here. Yeah, right. So 3 coordinates for the position of receiver, and 1 for this constant term, which is 4. So we will have 1 equation and 4 unknown. So how many Doppler counts we need? 1, 2, 3, 4, at least 4 to get a unique solution. And we have more than we will have. This is square principle to solve. The Doppler count, I write it again, Ji. This is a mathematical formula. And as we see here, there are 3 unknown positions here. And here we have one more position. So 1 more unknown to estimate on 4 equations. But it is not only, we can also have more positions. So for example, if we have antenna different places, and we have one satellite pass over this area, and we track each receiver track the satellite over this specific time. So they can determine their own position if they can see, or they can receive the signal from the satellite. That's a multi-station position. That's also possible. Another way, which is actually in the DORIS system. DORIS is Doppler orbitography radio positioning integrated system. It's a reference system, and the principle is the opposite to positioning at the land. So in fact, we have some positions, some stations on the ground with known coordinates, and they have stable frequencies, and they send frequencies to satellites. They send the frequency to the satellites, and the Doppler count is in fact counted here. In this case, the position of this beacons or of these stations are known with high accuracy, and the Doppler count these points can be regarded as known points, and the coordinate of the satellite and the orbit is unknown. Actually, this system is work for the low Earth orbiting satellites, not all type of satellites. And many of these ultimately satellite, they are equipped with DORIS receiver, DORIS antenna. So these signals from the different stations with the good global coverage send stable signals to the satellite, and the Doppler count actually is computed at the satellite. Or we can look at this system in another way. If I say that if I stand up somewhere and the car is moving in that direction, I see the Doppler count, Doppler shift here. Or I can say that, okay, the source is constant and I move in that direction. So I will get the same Doppler count. It's the same. The movement is a relative, is relative. So it is like, if, for example, if these points have this amount coordinate and they are constant here and they are sending the signal, actually, when I am moving towards this point, for example, I'm moving toward this point, then I receive different frequencies here. When I get closer, then I get high frequencies. When I get far, lower frequency. The same principle. But this time, instead of that the source is moving, it's the satellite which is moving. But the principle is the same. You can compute the Doppler counting. So since you have several stations, you can write different several equations for solving the system. And you can have the coordinate of this time the coordinate of the satellite is unknown. And you will compute the Doppler count from the satellite, Doppler count from different stations. Then you can determine coordinates of the satellite. Coordinates of the satellite at this position and the position. That's one method that's used for this orbit determination of lowest orbiting satellite by DORIS systems. And it is shown that the accuracy is rather high, up to 10 centimeters on up to 20, something like that. They can determine the coordinate of the satellite by this accuracy.